Assalamu alaikum, dear students. How are you? I hope everyone is doing well. We are back on chapter 4, section 2. Chapter 4, section 2 is about second derivative test. Second derivative test can tell us about concavity of a function. Concavity of a function is like this. When you look at a function, whenever the function is like this, it's called concave. And whenever the function is like this, it is convex. Finding intervals of concave and convex graphically is quite easy, but what if we have a function with no graph given? Then we need to follow these steps. Step 1, find the first derivative. If needed, simplify. Step 2, find the second derivative. And then to find point of inflection, we need to set second derivative equal to 0. Solve this to find x. Point of inflection is this point, which is located between concave and convex. Once we found the point of inflection, just like first derivative test, we can make a table, choose some values for testing. Then if the second derivative is positive, it's concave. If the second derivative is negative, it is convex. We can always relate this concave convex as follows. If the second derivative is positive, positive is happy, so it is concave. If the second derivative is negative, negative is sad, and it is convex. That's convex, and this one is concave. F double prime equal to 0 most of the time is point of inflection, while we have cases of f double prime equal to 0 and the point does not become inflection. We will talk about it later. Let's begin with a simple example. This example from the book is a very good example. Let's take the example to notebook and start solving. Here's the question. Simply the question says find intervals of concave and convex. In order to find intervals of concave and convex, we begin with f prime x. F prime x is the first derivative. 1 over 16 stays the same. Derivative of x power 4 is 4x power 3 minus 3 over 2 stays the same, multiply by derivative of x squared is 2x. Okay, now if you multiply, 4 divided by 16 will be 1 over 4, x power 3, minus 2 cancels 2, then becomes 3x. This is the first derivative. Now if I try to find the second derivative is equal to 1 over 4 stays the same, 3 goes down, I can say 3 over 4x power 2 minus 3. This is the second derivative. Stage 2 of the solution is to take second derivative equals 0. 3 over 4x squared minus 3 equal to 0. Let's send 3 to the other side, becomes positive. 3 over 4x squared equal to 3. Now multiply both sides by 4. 3x squared equal to 12. Divide 3, x squared equal to 4. Now take square root x is equal to positive negative 2. These positive negative 2 are points of inflection. Now to find intervals of concave and convex, we need to make a table. Now let's do it. To make a table, we need x, f double prime, and f. I need x, f double prime, and f to see if it's concave or convex. The smallest possible x for this polynomial is negative infinity. And then we have the first point of inflection is negative 2, and then 2, and finally infinity. We always choose numbers between these numbers written in place of x or in the row of x for testing. Less than -2 for testing, I'm going to choose -3. Always put the test numbers in squares so you don't write them in the intervals by mistake. None of these test numbers that I write in orange go into the intervals. The intervals should contain infinity, -2, negative infinity, -2, 2, and infinity. Now, I want to choose a test number between -2 and 2, and 0 is between them. It's a good number, easy for calculation. More than 2, let's say 3. Okay. These numbers should go into the second derivative. This is the second derivative. Now, if I put -3 in place of x here, -3 power 2 is 9. 9 times 3 is 27. 27 divided by 4 is definitely more than 3. When we subtract, we get positive. Positive is happy. So this interval from negative infinity until -2 is concave. Now, if I put 0 in place of x, I'll get 0 minus 3 will be negative, and negative is convex. If I put 3 in place of x, 3 power 2 is 9 times 3, 27 over 4. 27 over 4 is definitely more than 5. It's more than 6 as well. When we subtract it by 3, result will be positive, and positive is concave. Now, interval of concave, we have two intervals of concave. It is from negative infinity until -2, union with 2 infinity. In chapter 4, every single interval we write or we find are open. From negative infinity until -2, the second derivative is positive, but at -2, the second derivative is 0. So -2 is inflection because it is located between concave and convex. This -2 is inflection. Similarly, 2 is inflection. Why? Because it's located between convex then concave. If I have convex, the point between them will not be inflection. Or if I have concave, the point between them will not be inflection. This is concave, and let's write convex. Convex is this region, which is from -2 until 2. This is the answer. There you go. These are the answers. If I want to write point of inflection, this -2 I found is x. If I put -2 back into the original function, I will get -5. So the point -2, -5 is point of inflection. Similarly, if I input 2 into the original function, I'll get -5 as well. Then 2 -5 is also point of inflection. Point of inflection is only one type. It's not like critical point to be maximum or minimum. Point of inflection is only one type. It's just point of inflection. Let's solve another example. This is x power 4, and you know x power 4 has a W shape. W shape has like two pieces of concave and one piece of convex. Let's find the intervals precisely. Let's take the example to the notebook and solve it. All right. The question says find the interval on which the function is concave or convex. Okay. Since it's talking about concave convex, I know I need to find second derivative. In order to find second derivative, we begin with first derivative. F prime x is 4x power 3 minus 2 times 4 is 8x, and derivative of 1 is 0. Second derivative is equal to 12x squared minus 8. Now I need to solve second derivative equals 0. 12x squared minus 8 equal to 0. To solve this, I can send 8 to the other side. 12x squared equal to positive 8. Now divide 12, divide 12. X squared is equal to 8 divided by 12. 8 divided by 12 can be simplified to 4 over 3, 2 over 3. It has 2 fours and this is 3 fours. Or if you think you are a little bit nervous, in the exam always use calculator to play this safe. When you are nervous, you are not 100% yourself. Things that you find them easy, you might find them difficult when you are nervous. So I always recommend using calculator. Get used to calculator, be fast on calculator. Now I'm sure this is equal to 2 over 3. Now I have to take square root to remove this power 2. Then x is equal to positive negative square root 2 over 3. Okay. These are inflection points. Inflection points should go into the table so we can find intervals of concave and convex. In the interval, I need to have x, f double prime, and f. Let's do it. This is for x, this is for f double prime, and here f. The x, least possible x or smallest x in the list is negative infinity. And then we have negative radical 2 over 3, and then positive radical 2 over 3, and then infinity. A number between them for testing is 0. A number more than radical 2 over 3, again play it safe. Radical 2 over 3. Last answer I had was 2 over 3. Radical 2 over 3 is 0.8. So 1 is an easy number for input into the second derivative, and on the side negative 1. Okay, I always put the test numbers into squares so I don't write them in the intervals by mistake. The intervals should contain infinity and radical 2 over 3, positive negative. Okay, put negative 1 into the second derivative. F double prime negative 1 is equal to 12 times negative 1 squared minus 8, and that's obviously equal to 12 minus 8, which is 4. 4 is positive. I only need the sign positive, means happy concave. If I put 0 into the second derivative, f double prime of 0 is equal to 12 times 0 power 2 minus 8. Where did I get this? This is the second derivative here. That's equal to negative 8. I don't need the 8, I only need the sign. Negative is sad, which is convex. And finally, if I put 1 in place of x, again it will be 12 times 1, 12 minus 8 will be positive, and positive is happy, that is concave. Now let's write the intervals, as the question asks for intervals only. Now concave has two intervals, negative infinity until 0, both open, union with, oh no, 0 should not be in the interval. 0 is a test number. I have to write radical 2 over 3 negative. Union with radical 2 over 3 positive until infinity. This is why I always put the test numbers into squares so I don't write them by mistake in the intervals. Okay, these are intervals of concave, and for convex, convex is only one interval which starts from radical 2 over 3 negative until radical 2 over 3 positive. Then this is the interval of convex. Answers all available. Okay. Graphical questions. In exercises 1 to 4, identify the open intervals. So we have to write open brackets on which the graph of the function is concave and those on which it is convex. This graph is one piece of concave, then this function is just concave on all real numbers or concave on negative infinity to infinity. This graph is concave and convex. The point right between concave and convex is here, it's between them. It's equidistance from the top and the bottom of the function. Then from negative infinity, this side is negative infinity, until 0 is concave, from 0 until positive infinity it is convex. Remember, we always write x in the intervals, we never write y. I never write -2. In the multiple choices, there is definitely a choice that contains -2. It is a good number, it's y-intercept, but I don't need to write y in the intervals, only x. So concave is from negative infinity until 0. Convex is from 0 until positive infinity. This is convex, this is concave. Another graph. This piece of graph is concave or convex. It's obvious that this graph is concave. If you are not sure, just symmetrically complete the graph. If I complete the graph like this, isn't this definitely concave? On the other hand, this is concave. If the completed graph is concave, then the graph that is given is also concave. Now, as you see, we have two intervals of concave. This line here is located between concave and convex. This line here as well, these are vertical asymptotes. So concave is from negative infinity until this line. This line is -1. If there is no point of inflection like this question, then vertical asymptote will be the borderline or the last number in the interval. Union with, there is another interval of concave which starts at 1 until infinity. Now concave is complete. Convex, convex is between these two vertical asymptotes. So convex is from -1 until 1. Now let's look at this graph. This graph, there are two pieces of concave and two pieces of convex. You might wonder where. Let's zoom this in and make the instructions clear. There is a little bump here. This bump is enough to say convex. And there is a little dimple here. The curve went down a little bit. Went down a little bit is enough to say concave. And this part is obviously concave. This part of the graph is obviously convex. Now let's write them as intervals. Let's identify some point of inflections. This point of inflection is located between concave, convex. That's one point of inflection. And there are two other points of inflection. One of them is here. This part is concave, this one is convex. Another point of inflection is right here. Now if I write it as interval, negative infinity until -2, this is concave, union with 0 until 2. These two intervals together are concave. Now convex. Convex is starting on -2 until 0, union with 2 until positive infinity. Look at 2, this 2, the x, until positive infinity. This graph is convex. Okay, this is enough for this lesson. Thank you so much for watching. In the next lesson, we're going to solve the exercises of chapter 4, section 2. Thank you for watching.